Hi, I'm Bob Schleicher. I'm the Vice President of Product Development with DiCon LED. LEDs are becoming much more prevalent in lots of lighting applications, and recently you're starting to see the use of LED lighting in plant growing applications. So what I'd like to talk about today is a little bit of LED basics, as well as some discussion of why DiCon LED's LED technology, how it differs from traditional approaches and some of its advantages. What is an LED? The acronym stands for light emitting diode. Fundamentally, an LED looks like any other sort of diode electrically. It passes electrical current in one direction and not in another direction. And like any diode, LEDs are fabricated by combining P and N type semiconductor material to form a PN junction. The difference between an LED and another type of diode is that when electricity is passed through that PN junction in the forward direction, an LED emits photons of a particular wavelength. An LED chip is a narrow band light source, and by that I mean it doesn't produce light over the whole visible light spectrum. It produces light over a fairly narrow band of wavelengths. So you'll have red LEDs, and actually different shades of red LEDs, blue LEDs, green LEDs, and so forth. LEDs have been around for a long time. They were invented decades ago. But throughout the years, and especially in recent years, there have been tremendous and dramatic improvements in the efficiency that LEDs have at converting electrical energy to light energy, and also in the amount of brightness that a single LED chip can produce. So now you see a lot of people talking about high brightness LEDs as opposed to sort of normal lower output LEDs. A typical high brightness LED chip will be about 1 millimeter on a side as a bare chip. And in the photograph at the bottom, you see a number of LED chips of various colors compared in size to a penny. LEDs don't typically radiate heat or infrared energy unless they're actually designed intentionally to do so. But nonetheless, the conversion of electrical energy to light generates heat at the chip level. So thermal management of the mounting of LED chips is important, but when thermal management is done properly, LED chips can last for a very long time. Typically, you might have LED lifetimes of 50,000 hours, which is around 5 years or a little bit more. All LEDs are not the same. Typically, to get the kind of light output levels that we're talking about with high brightness LEDs, there's a variety of tricks that are played. Surface patterning on the top surface of an LED chip can greatly increase its light output. And more specifically, make sure that the light that is emitted from the surface of the LED chip is emitted in a more vertical direction. Top LED manufacturers all have, highly proprietary surface treatment and photon extraction processes and the little tricks that they all play to produce high brightness LED chips, and that same thing is true for DiCon LED. A lot of times LED chips end up being binned by light output. The manufacturer will make a lot of chips, and based on testing will determine both the wavelength as well as the amount of light produced by different batches of those chips. The brighter the chip, the more they cost. I mean, that's just a basic of the marketplace. The LED chips used in Kessil lighting products are produced by DiCon LED, which is a California-based company, with our own fab for manufacturing LED chips at the wafer level. And some of the photos here show scenes from our LED fab. Another element that's very critical for making high brightness LEDs is chip bonding. And by that I mean the bonding of that bare LED chip to some form of substrate or chip carrier that it rests on. There's a variety of fairly low cost bonding methods out there that have been used traditionally for single chip LEDs or single chip LED cells. And typically a an LED chip would be mounted using an epoxy or some form of glue on either a regular printed circuit board or perhaps a little ceramic based chip carrier with leads attached to it. The process is fairly simple for doing this. Unfortunately, epoxy, when used to attach the die of the LED chip, does not transfer or dissipate heat very well, so there are some thermal limitations of this approach. And the ceramic that's underlying it, or the PCB material that's underlying the chip and providing structure for it, is also not very efficient thermally. This shows a high reliability bonding method as used at DiCon LED. In this case, an LED chip is bonded through a metallic bonding process, through a series of metallic layers, to a metal carrier. And so by using metal both for the bonding process as well as the underlying carrier, there's tremendous thermal transfer of heat from the bottom of the LED chip down through these layers to potentially a heat sink at the bottom of the metal carrier. This is, at least a fairly typical method for professional grade products. The cost is somewhat higher, but yet the advantages in light output and thermal efficiency are tremendous. And all of Kessil's products use this metallized bonding process for high thermal efficiency. There's also some differences in packaging LED chips into usable light cell elements. The most typical method for doing this is to use single chip packaging. In this case, an LED chip is mounted in some form of a reflective cup on a little chip carrier. This shows an example. And a fairly simple lens will be mounted on top to both provide some focusing of the light as well as to seal the bare chip from the outside elements. For cost reasons, this lens is typically made of a plastic material. One of the disadvantages of that is that over time, over many hours and even some years of use, you can get yellowing or darkening of that plastic lens material, leading to a loss of light output. DiCon LED takes a different approach. We put large numbers of individual high brightness LED chips in a very densely packed array of chips. This shows a close-up of an array made up of red, green, and blue high brightness LED chips. 21 chips in all. And those are packaged under a single lens. Because we're using only one lens for a collection of 21 chips, we essentially can afford to make it out of a better material. So the lens is made out of high quality optical grade glass. Underneath, as mentioned in the last slide, a metal bonding process is used to cement or attach the LED chips to the carrier, and the carrier itself is primarily made out of metal. So again, there's tremendous thermal transfer out the base of the product. And this shows a completed array, in, again, a 21 chip array in this example. Some more thoughts on thermal management as well as the drive electronics needed for LEDs. As we've talked about already, thermal management is critical for getting the most out of your LEDs and LED arrays. It's not just a matter of getting rid of the heat and ensuring normal operating temperatures. It's also true that if the LED chips are operated at higher temperatures due to poor thermal management, their lifetime and light output negatively impacted. So not only do you get less light, but the amount of light you get over time declines much more rapidly if the chips are running too hot. So it's very critical to do good thermal management, and that means in the case of DiCon LED products, the metal bonding process, the metal carrier, and then a heat sink underneath that metal carrier with a small fan to blow cool air across the heatsink and to get the heat out. Another critical issue, though, is the control electronics for the LED chips. LEDs like to see a constant current, and so one of the basic functions is to take wall voltage in the form of 110 volts AC and to convert that into a DC current a constant current that's fed through all of the LEDs at the same level. The control circuits to do that need to be efficient because, you know, in the end, what the consumer cares about is how much light do I get out and how much do I have to pay for the electricity to run the product. And by using very efficient electronic driver circuits, as well as getting good thermal management so we can run relatively large currents through the LED chips, we get the most possible light output with the lowest possible number of watts put in from the wall. Now there's a lot involved in making an effective LED lighting product, and one of Kessil's key strengths is the level of vertical integration that's brought to the table with every Kessil lighting product. So there's a commonality of design and coordination amongst various teams to produce not only the final product, the light fixture, but the subsystems that are part of that product, including driver electronics and control boards, as well as various mechanical parts that are associated with the thermal management of the product. Through the use of DiCon LED light cells, the vertical integration extends also to the source of light itself. In this case, a dense matrix LED with 21 chips, and in some other cases even more, up to 50 or even higher. That's a highly integrated product that uses, to begin with, very advanced high brightness LED chips that themselves are manufactured in DiCon LED's fab. So by controlling every step of the process and the various disciplines involved of electronics, thermal management, materials, optics, and mechanics, we can ensure that all the pieces fit together perfectly and that the whole product, the Kessil lighting product, is greater than the sum of the parts that went into it. This just tries to summarize some of those key differences that we've just spent time talking about between Kessil lighting products and then what's typically done in the industry. Fundamentally, we're using DiCon-made ultra-high brightness chips, not just whatever we can source off the open market. Key advantages in terms of chip bonding through the metallized chip bonding process, the use of a high-density LED array on this patented metal circuit board, very well thought out and executed thermal management. Because of the sophistication of the metal circuit board at extracting heat to its base, we actually get very good thermal management just by using a simple heat sink and fan. The combined system approach results in excellent reliability, partly attributable to the use of that metal bonding process so that the operating temperatures of the LED chips is kept at a minimum, and as a result they last longer and maintain maximum light output for a longer number of years. The use of a single reflector over the entire array means that the light output from all the chips that are part of that array is very well mixed together, leading to very highly uniform and focused intense light. And that in turn means that we get good penetration of that light into the plants that are being grown. The other key advantage of having many chips combined in that tiny space, roughly the size of a dime, is that our overall lighting product is extremely compact, and that provides tremendous flexibility for mounting the grow lights as well as their use. I hope I've been able to explain some of the basic concepts behind LED technology and also some of the differences that exist between approaches taken by a variety of companies. Hopefully this will help you to understand the key advantages provided by Kessil lighting products and why they're being greeted with so much enthusiasm in the marketplace. Kessil lighting, by virtue of the latest technology from DiCon LED and the use of the dense matrix LED, is truly leading a spectral revolution in plant growth.